Welcome back friends, and welcome to the last lecture of this entire series, okay, where we are dealing with quantum mechanics in the relativistic sense essentially. And along the way we learnt a lot of stuff essentially, we learnt various things essentially, and then we are dealing with the last topic of the course essentially, which is dealing with relativistic corrections to non-relativistic systems. And along the way I said that there are these states which are very well understood in the non-relativistic framework, which are called bound states essentially, which are very well bound states, which cannot be completely understood very well in a relativistic framework essentially, in a relativistic framework. So to deal with so we will deal with this framework. So like I said, what we will do is what we will do is we will derive non-relativistic bound states. So to deal with, what we have to do is we have to consider non-relativist reduction of say fermions essentially. In the case of if you have Dirac equation, you take the non-relativistic direction of the Dirac equation in the presence of electromagnetic field, and then you derive the possible most general expression possible with corrections which are of the order of p square by m essentially. So in the non-relativistic reduction, the main point is the mass is the dominant term, and that is the point we had trying to do essentially. So to begin with, we started with one of the first reductions we did was just choose a particular wave function essentially with that m to be the rest mass, which is a very large limit, m to be the large limit, and m to be larger than 2 if we add all the potentials essentially. And we take this m to be much larger than the t, which is nothing but the kinetic part or the p square part or the mass the difference between the relativistic and non-relativistic energies essentially, and then it is greater than the momenta, it is greater than all the potentials essentially. So greater than all the potentials. Now given this large limit, and we try to derive it, and we end up having the Schrodinger equation. So after derivation essentially we take this, put it back into the wave function, and we see a Dirac wave function, a Dirac equation, and we see that the thing is sort of the lower component is much smaller than the higher component essentially. And so what we do is we solve the 2 in the large m limit and put it back in 1. That gives you that Schrodinger equation with Pauli terms. So this is all consistent. We have Schrodinger equation, the non-relativistic limit of the Dirac equation is Schrodinger equation with Pauli terms, and the Pauli terms tells you that the existence of, it's a spin half particle, and it has a gyromagnetic ratio of 2 essentially. All of them is consistent, but still this is not completely the real picture, because you do not really have the p square by m square kind of terms essentially, or p square by p cube, the higher order. You do not have a systematic expansion in terms of the relativistic corrections to this process and to this Hamiltonian. This is good, but one does not have a systematic expansion in terms of all the relativistic effects essentially. One does not have a systematic effects expansion of all relativistic effects. So to derive relativistic effects means in the order of p square by m, p square by m square, various essentially. To the Hamiltonian it will be p cube by m square, so on, so essentially. To derive this, what we would like is to start with the Dirac equation and the Dirac Hamiltonian, okay, and then apply a unitary transformation such that it gives a systematic expansion, order by order expansion in terms of the relativistic corrections essentially, and such a transformation is called a Foldy-Wuthieson transformation. It is a unitary transformation, it is a unitary transformation, and the construction of the transformation is simple essentially. So the construction of a transformation is nothing but you start with the, so this is your Dirac Hamiltonian, you have written the two component form, this is the energy term, the mass, and A0 and m times beta essentially. You write it in this particular fashion and you define your Foldy-Wuthieson transformation in this particular fashion, some beta times lambda by b alpha bar times p bar essentially. Okay. So, beta alpha times b lambda bar times beta essentially, okay, lambda bar times p bar, where A tilde is given by p square by m square times a 1 minus p square by m square times a lambda square, a parameter essentially. And this is a unitary transformation, this is UU dagger is equal to 1 essentially, this is a unitary transformation with UU dagger is equal to 1. Okay. So, this unitary transformation now you have to do with, now you can apply this unitary transformation in how many orders you want essentially. You can order it, apply it once, you can apply it twice, you can apply it several times, such that for each order you get a one correction, one relativistic correction essentially, one order of magnitude. So, higher and higher relativistic corrections if you want, you have to apply it so many times essentially, so many times. So, what you do is you have u t chi prime eta prime h u inverse chi prime eta prime is equal to h prime chi inverse eta prime. So, this is one application, one times you apply the u. U is a unitary transformation, H is a matrix, it is also so it has to be applied both the times, both the sides essentially, and then you can evaluate it. So, you can evaluate it, it gives you some terms essentially, you can evaluate it this particular fashion, okay, and each term will give you some form essentially, and at the end of the day after the first iteration it gives you I will write this expression because deriving is a lot of time essentially, h 1 prime is equal to V0 minus p square by 8 m square V0 minus V0 p square minus 8 m square plus sigma dot p V0 sigma dot p by 4 m square plus 1 by 2 m sigma I think we use the notation A0 this should be A0 sorry A0 sigma dot p minus a bar sigma bar dot p bar plus sigma bar dot p bar sigma bar dot p bar minus a bar minus p power 4 by 8 m cube minus p square by 2 m. Okay. So, then you have to solve it again, essentially you have to make further simplifications, and further simplifications finally the final answer essentially after taking various aspects essentially this will give you the final answer So, this is your Schrodinger equation, again your Schrodinger equation with higher momentum terms, essentially higher momentum terms, higher derivative terms essentially, with the corrections, full relativistic corrections after doing the relative, and each of them will have an effect essentially, each of them will have an effect essentially. Okay. So, each of them now will have an effect. So, now we will see how each of them will affect the spectrum. Now, we will not do the full derivation and everything, it will take several hours of derivation essentially this will. Okay. So, what I will tell you is how each term will have an effect essentially, how each term will have an effect. So, let me highlight each term essentially. So, how each term gives you an effect essentially. So, each of these terms contributes to the change in the spectrum of the hydrogen atom, change in spectrum So, the relativistic corrections to the hydrogen spectrum are, the first one is the fine structure. The fine structure is okay, and it is so it gives you the main thing essentially. So, the main two things which give are essentially your fine structure and Zeeman effect, both of them are there essentially. So, the fine structure comes from three terms. So, one is p power 4 by 8 m cube. So, this is relativistic mass increase, and then there is this other term which is called 8 m square del square phi. This is nothing but E 8 m square del dot z, this is nothing but z e square by 8 m square delta of r. This is called the Darwin term. So, this is this term. So, in this bunch of all these terms which we wrote down, this is the Darwin term. Okay. This is the Darwin term, and then the first one is relativistic mass Darwin term, okay, and the third term is the spin orbit term. And the third term is the spin orbit term, which is so this is nothing but E by 2 m. called the spin orbit term. So, this is this term. So, how many things? You have the relativistic mass term, you have the Darwin term and the spin orbit term. So, the Darwin term contributes only to L is equal to 0 states essentially. Okay. And the spin orbit term is the correspondence of the Thomas precession, which we learn essentially in our classical electrodynamics. Magnetic moment, okay, the magnetic moment of the electron interacts with the motion and automatically leads to the spin essentially in the thing essentially. So, this is nothing but your interaction of the magnetic moment with the magnetic field. Now, where does the Darwin term come? The Darwin term is because of the zeta bit Weak-Gang. Okay. You see that oscillations which are very rapid essentially, it comes with position of the quantum fluctuations. Around the position of the electron wave function. Okay. So, finally, we end up having the final things as essentially this is equal to minus m, energy is equal to z alpha by 2n square minus m z alpha by 2n power 4 n by j plus half. So, this part gives you your fine structure essentially, this part gives you okay, this part gives you your fine structure essentially, fine structure of the hydrogen atom essentially. Now, there is also one more term which is nothing your standard Zeeman effect essentially, which we know in your ordinary quantum mechanics. So, this is sigma dot b term essentially. Okay, sigma dot p minus a, essentially this will give me p minus a terms and b plus l essentially p dot a and p dot t, and that gives me your Zeeman effect. So, what we have is these three terms which contribute to your relativistic, the other terms contribute to your Zeeman effect essentially. Okay, the Zeeman thing essentially. So, this contribute to your and the entire contributions can be written in this particular fashion, which is nothing but the fine structure constant essentially, which is nothing but your fine structure constant. Very well, but there is still one particular contribution. So, you have seen that there are all these contributions which you can calculate, relativistic calculations which you can use to compute your fine structure constant of the hydrogen atom, and they are all coming from relativistic effects, and you can systematically calculate them by using this Foldy-Wouthison unitary transformation, applying on the Dirac Hamiltonian, and then get this all these corrections and compute the spectrum. And the computation of spectrum is quite involved. Actually you had to solve this equation and the corresponding bi-LMs and spherical harmonics carefully essentially, and then you end up having the spectrum finally essentially. But there is also one more effect which happens, which cannot be explained by this by the relativistic effects. Okay. The fine structure of the hydrogen atom you can explain it by computing all the relativistic corrections and so on. So, but there is also one more tiny splitting which is almost 1/10 of the splitting of the relativistic the fine structure constant essentially, fine structure splitting, which you cannot explain by this method essentially, which you cannot relativistic corrections which you cannot explain, cannot be explained by the relativistic corrections of the Dirac equation. And for that you need the quantization of the electromagnetic field. So, you need the quantization of the electromagnetic field, and so you have to compute the quantization of the electromagnetic field, and this involves really quantization of the electromagnetic field and the mass renormalization essentially. So, it has some what you call regulation effect, regulatory effects essentially. It really, so you have to really quantize the electromagnetic field, and you also have to what you call take the effects of the radiation of the quantization of the electromagnetic field, which the quantization of the electromagnetic field which leads to infinities, and these infinities have to be absorbed in the renormalization of the electron mass So, you have to do this essentially, and you have to absorb the renormalization of the electron mass, and this is really a full quantum field theory calculation taking into consideration the quantization of the electromagnetic field, okay, taking into consideration the electromagnetic field and then doing a renormalization essentially, and doing all that. This effect is seen, and this effect is called the famous Lamb shift. Now again, you remember that this is a non-relativistic system, the hydrogen atom is a non-relativistic system, but there are quantum field theory effects in a hydrogen atom. Essentially there are quantum field theory effects which are tiny, very tiny, but they can be observed essentially, they can be observed, and the calculation is quite involved essentially, but there are very famous people who seems to have done it very fast essentially, okay, like Bethe is supposed to have done it in an airplane essentially. So this observation, the change in the energy essentially is given by delta E lamb, it's called the famous lamb shift, is given by z alpha square 4 by 3m square mod psi 0 square log E max minus large E max by E. Okay. So, this is the formula. It comes out to be a simple formula at the end of the day, but the calculation is quite detailed, essentially quite detailed, and this is the transition between the two same j levels. The j levels are same, transition between two same j levels. So, this transition is very small compared to the fine structures. So, it requires full quantum field theory technology for non-relative systems. The computation is called now. Okay. To summarize, okay, so let us look at the spectrum of the hydrogen atom. So, I will leave you with this spectrum essentially of the hydrogen atom. So, first okay, let me label this. So, 1 as half and this is hyperfine splitting 1420 megahertz. This is 2 as half and this is 3 as half. This is 2p half and this is 2p 3 by 2 and this is fine structure. Okay. This is roughly 10 times that of lamb shift. And where is the lamb shift? The lamb shift is between these two, between 2s1 2 and 2p half essentially. So, this is the lamb shift. Okay, this is the lamb shift. So, this is the lamb shift. Okay, this is the fine structure essentially. So, this is a fine structure. this is the fine structure, this is the lamp shift. Again you will have one more here. So, here is also a lamp shift. And this maybe between 3s1 and 3p half. And then there is between 3d 3/2 3d 5/2. So, there is a lamp shift essentially. Okay. So, here is a fine structure which is a large effect which is coming from this thing. There is a hyperfine structure here at this particular point, and then there is the lamp shift which is extremely small essentially. So, this in fact is sort of the calculation of this, and observation is in fact is the high point. Of course, there are other things like positronium and quarkonium is really the high point of our course essentially. This is the high point of our course, that we have managed to reach the point that we can see some observable effects essentially of these relativistic effects in atomic systems, in non-relativistic systems. Of course, there are relativistic cases we have already seen, like scattering, Baba scattering, electron scattering and physical process, but the lamp shift is such a wonderful thing that you have quantum field theory or whatever quantum mechanics in the real sense is actually the quantization of the electromagnetic field which plays a role in giving the splitting assumption. There is no other way which you can have, and you need to use the techniques of renormalization and everything which we talked about in this course to actually calculate this essentially, to actually calculate this. And the typical techniques people used were the techniques which we talked about, which are old things, but even today these are the same techniques which are used to calculate the effects which we are talking today. But if you are talking about high energy collisions and high energy renormalizations, you can use the full quantum field theory and everything essentially. Okay. So, to summarize in this course, we first learned about the requirement of we studied the how things change, how particle interpretation changes from one particle states to multi-particle states in relativistic quantum systems. We studied the Klein-Gordon equation, we studied the then we studied its solutions and its non-relativistic reductions, and then the interactions, the interpretations. We studied the Dirac equation and how it is connected to the Lorentz group. How you can explain the Dirac equation in terms of the Lorentz group, because how the Lorentz group, what are the spinors. We wanted to understand what these wave functions are, the new wave functions which we ended up with. We looked at the covariance of the Dirac equation under Lorentz transformations. Then we looked at bilinear covariants and how to introduce interactions into the Dirac theory, and then we took that simple interactions like QED interactions essentially, and then we used the propagator and Green's functions methods to, because we said that the problems in using just quantum mechanical methods will have problems. So, instead of that we use the Green's functions method to derive the propagators and then solve this, and we showed that the propagator methods give you the correct answers to deal with multi-particle states. The propagator inherently has multi-particle states within it, because the propagator is a combination of several states essentially. Okay. And so, all the Klein paradox and problems like Z-Rotator gang are gone the moment you use the propagator methods essentially. and then we used it to compute simple QED process, and finally we talked about bound states, and then from bound states we looked at the non-relativistic reduction and the relativistic corrections to bound states, and the example we have chosen is the hydrogen atom. So we have covered many of the aspects first as a first course when we are dealing with relativistic effects in a for a relativistics in a quantum mechanical regime. And if you have any questions, you are welcome to contact me and my students and who have helped me in this course essentially. And it has been wonderful for me to take this course, and I thank you all for the interaction session and for taking this course. And I hope I will come back again to give the next level course on quantum field theory 1 hopefully next year essentially. Okay. Thank you very much for being with me and listening to this course. I wish you all the best for your final exams, and I hope you do very well in this course. Thank you very much.